In this lesson, we'll learn how to take limits of functions without having to switch over to numbers. We also won't really need the pictures anymore. First off, let's start with some basic limits. And these limits are pretty easy to derive using the epsilon delta rules, but to make it simpler for our case, let's just look at a justification of these. To put this in words, the limit of a constant is just the constant itself. If you take the limit of x, you can do direct substitution and just get the value c. Similarly, if you take the limit of x to the n, you just get c to the n. So for x and x to the n, it's just direct substitution. Just for a quick justification of the second one, let's consider the line y equals x. Looks something like this, and let's just pick a value c. Well, at that c, we've got the limit as x approaches c. So we're going to look as the x values are approaching c from the left and the right, and look at what the function values are doing on the curve from the left and the right. As you probably know, if it's the line y equals x, then the y coordinate here is c. So the function values are approaching c as x approaches c, and thus, as we said, the limit is actually c. Here's some properties of limits, and all of these would need to be proven using the epsilons and deltas, but we will not do that for this particular class. The properties of limits have a few things here. We've got a scalar multiple. All that really says is that if you take a limit with a constant in front, you can bring the constant in front of the limit. If you take the limit of a sum or a difference, you can just take the sum or the difference of a limits. If you take the limit of a product, you can just look at the product of the limits. And similarly for quotients, as long as the denominator is not 0. Similarly for powers, and even for roots, as long as the inside is positive when the root is an even root. This gives us a lot of different powers. So what we ought to do is try a couple of examples and see if we can make sense of here's some ideas of how to take limits. I will give you a word of caution first, in that these limit laws, as we call them, are not able to just generally be used on any sort of thing, but for limits, you can take a limit and break it over a sum, a product, a difference, a quotient, but don't assume that this works for all of the things we're going to do in calculus. Here's our first example. We're taking the limit as x approaches 2 of this fraction. So the first thing we can do, and I'll write this out step by step the first time, is we can break the limit across the quotient. We have the limit as x approaches 2 of 2x squared plus 1 over the limit as x approaches 2 of x squared plus 6x minus 4. Because we can break it across a quotient, this will be valid as long as the denominator does not end up being 0. The next thing we can do is break it up across sums and differences. So let's do that next. This looks a little bit lengthy, but we're only going to do this once. Limit as x approaches 2 of 2x squared plus the limit as x approaches 2 of just 1. And then we'll also do the same down here. Limit as x approaches 2 of x squared plus limit as x approaches 2 of 6x minus the limit as x approaches 2 of 4. So these are what our limit laws give us the power to do. First, we were able to break it up across a quotient. Now we can do it across sums and differences. We'll do one more step and then we can get the final answer. Another rule is that you can break it up across products, constant multiples. You can bring these in front. We get 2 times the limit as x approaches 2 of x squared. Plus, I'm going to go ahead and use this. I said that the limit of a constant was the constant. So when I take the limit as x approaches 2 of 1, I just get 1. This one I'll leave alone. Limit as x approaches 2 of x squared. For the next one, I can bring the 6 in front. And then again, the limit of a constant is just the constant. Notice my answers aren't 2 for these things. It's just whatever number's in there. Now, we're finished with this problem as soon as we use the last couple of rules. We did say that if we took the limit as x approached a number of x to a power, it was just that number to a power. So we get 2 times 2 squared plus 1. And then again we can do the same thing. 2 squared. The limit as x approaches 2 of x, as we showed, was just 2. So plus 6 times 2 minus 4. If we calculate this, it looks like we get 9 over 4 plus 12, 16, 12, which is 3/4. And that's the value of the limit. Previously, we were required to use a graph or try plugging in values close to 2. With this strategy, we don't need to do anything but just plug in values and use our laws. Now, as you might notice, this really, at the end, did just look like I plugged in 2 for x. More on that later, but for now, let's just pay attention to the fact that we use the quotient rule, the sum and difference rules, and we also use the constant multiple rules. Let's go to the next example. For this one, we have a product to deal with. So all I'm going to mention here is we do have products. We also have a power. We have some sums inside the parentheses. And then we've just got an x squared and an x, which I said was just plugging it in. Now I have limit laws for all of these. So this is the shortcut. As long as you can break it down and say it's just powers, products, quotients, sums, and differences, and maybe roots, you can just directly substitute in as long as you never get a denominator of 0. At least in these simple cases. We simply get -1 squared plus 1 times -1 plus 3 cubed. So we get 2 times 2 cubed, which is 16 for this one. The next one has a root. You'll notice this problem has a star beside it, which means it's a problem for you to try. Feel free to pause this video and see if you can take care of this root yourself. Okay. We've got roots. We've got a sum. We've got a constant multiple. All of that's present. So again, because of that, as long as we don't get a negative number inside the square root, substitution is again fine. I get -2 to the 4th plus 3 times -2 plus 6. We get the square root of 16 minus 6 plus 6. That's just the square root of 16, which you know to be 4. In general, we've got some ideas here, and I've got it written down here at the bottom of the screen. Any polynomial, any rational function with the denominator not being 0, we immediately get direct substitution because polynomials really only have quotients, products, powers, constant multiples, etc. This is actually also true for your trig functions, and we'll talk about the idea of a continuous function soon. You can always make a substitution for any continuous function. The next type of problem is a little bit more complicated, and these are the ones that I was hinting at. You need to do a little more than just substitute. This is the strategy. This is what we call the cancellation fact. If two functions are the same except at one point, then they have the same limit. If you look at the next example here, we've got x minus 1. And as you can see, if you plug in 1, you're going to get 0. Zeros in the denominator are not allowed. With that said, we cannot just use direct substitution. What can we do? Let's get a little inspiration from looking up here with plugging in 1 also. 1 squared is 1, plus 2 is 3, 3 minus 3 is 0. So we get 0 over 0. Anytime you see 0 over 0, that's a great time to use one of the two algebra techniques that I'm going to show you. This one is factoring. I'm going to factor the top to be x plus 3 times x minus 1 divided by x minus 1. Now you see what happens. We get some cancellation here, which is why this is called the cancellation fact. When we cancel this out, we get a new expression, just x plus 3. Now this was not defined when x was 1 previously, but even though it's a different function, it only differs at a single point, namely 1. Therefore, the limit is the same. So we get the limit as x approaches 1 of x plus 3. And now we can simply use the direct substitution. 1 plus 3 equals 4. So in this case, 0 over 0 turned out to be 4. Now, the next problem here is a starred problem. So remember, the starred problems mean those are for you to try. So in the case of this video, just go ahead and pause the video and give it a try if you want. And as soon as you get finished, resume and I'll show you what I did too. Okay, now that you've got some sort of work for this, let's try it ourselves. Again, factor. X squared minus 4x, I can just factor an x out. And in the denominator, this is x minus 4 times x plus 1. So again, we can cancel out the x minus 4's. And due to the cancellation fact, the limit is the same. We get the limit as x approaches 4 of x over x plus 1. And now, because of the quotient law and the sum law, we can just say this is 4 over 4 plus 1. And so the answer to this one is 4/5. 0 over 0 can be anything. If you plug in 4 here, you will find you again get a 0 over 0. Here's a strategy. Play around with your limits. Learn what can be done by substitution and what cannot. So really all that boils down to is if it's something fairly simple, no zeros in the denominator, no negative square roots. Otherwise, when you make substitutions, it's perfectly fine. If you can't do it that way, we've got the cancellation technique that I mentioned. This one that I'm about to do is a similar cancellation technique, but it's a totally different looking one. You will end up canceling something in the end, so let's see what happens. What I'm going to do to this one, there's really not any factoring that I can do. But if you plug in 0, you quickly see that I get 2 minus 2, which is 0 over 0. It's still the 0 over 0 case. For this particular problem, when you've got a square root, what you do is you multiply what's called a conjugate, which means take this symbol, in this case the minus sign, and change it to a plus. We're going to multiply top and bottom by this. What happens when you do this is that you still get another limit, but this time, if we multiply this out, we get x plus 4. The outer term is 2 times the square root of x plus 4. The inner is negative 2 times the square root of x plus 4. So they cancel out. And then I get a minus 4 from the last term. And the denominator, I'm not going to multiply it out. I'm just going to write it. And here's what you notice. The plus 4 and the minus 4 cancel. So let me just write this one more time before I move on. I get x over x times the square root of x plus 4 plus 2. With that said, now I'm using the cancellation fact. The x's cancel out, and I'm left with the limit as x approaches 0 of 1 is what's left when I do the cancellation. Square root of x plus 4 plus 2. Plug in 0, and I get 1 over the square root of 4 plus 2, which you guys can see is 1/4. Next example. I'll go ahead and mark this like a star problem. Feel free to try this one real quick. So pause your video, if desired, and do the same thing. This time it's in the denominator as to what you're going to change. So this time I would multiply by something related to this denominator term to see if you can make cancellation happen. Okay, now that you've possibly tried this, let's see how you did. We're going to do the square root of x plus 2 as my multiplier on the top and bottom. And so I get the limit as x approaches 4. And let me go ahead and factor this as x times x minus 4 while I'm at it. And then I get the square root of x plus 2 as the other term I just included. In the denominator, the first term is x. The outer and inner terms cancel again. And the last term is minus 4. Same thing, cancellation fact. We get the limit as x approaches 4 of x times the square root of x plus 2. Plug in 4, we get 4 times the square root of 4 plus 2. So that's 4 times 4, I get 16. Next thing that we can use to help us calculate limits is something called the Squeeze Theorem. Now this one is one that is for very specific types of problems. If you look at this function, we've got sine of 1 over x. Remember, sine of 1 over x is when we had what was called uncontrolled oscillation. For sine of 1 over x, the limit did not exist. However, for this one, with x times the sine of 1 over x, I'm going to use the Squeeze Theorem to prove that it actually does exist and even give it a value. And we'll look at a picture on the next slide. Here's the Squeeze Theorem. If you've got 3 functions, and g, the function that you're taking the limit of, is in the middle, and you've got a lower function and an upper function, so that the two lower and upper have the same limit, then the limit of the middle function is the same. So the idea is that it's squeezing down. If the limit of the above and below is the same, then the middle one has to be the same. So here's the usual strategy for this. The first thing I'm going to do is get a bound, some bound on this. It's not of the whole function, but it's a bound of some kind. As you know, the sine function stays between -1 and 1 from your pre-calculus course. It's bounded by those two values. All I have to do to make this look like my function is multiply through by x. Now I will be kind of technical here. I am sort of assuming that x is positive right here, but this will work exactly the same if x is negative. So we won't go any farther than say if it's negative, it's similar. Anyway, I have the function that I'm trying to take the limit for. I have an upper bound and I have a lower bound. So let's take the limit of the upper bound and lower bound. Limit as x approaches 0 of -x is 0. Limit as x approaches 0 of just x is 0. What we get is these two limits are equal, and therefore, thus, by the Squeeze Theorem, we get the limit of the original function. Limit as x approaches 0 of x sine of 1 over x is that same value, 0. That's the Squeeze Theorem. It probably looks a little bit complicated right now. Here's what's really going on. The graph of x sine 1 over x looks like this. But you've got x and you've got -x. And the sine of 1 over x, if you recall, has this uncontrolled oscillation thing going on. But because of these x multipliers, as you can see, the density thing does happen, but it now converges toward that 0. The Squeeze Theorem. The fact that it's between x and -x is what gives this to you. But let's take a look at a general summary of how this is easiest to use. Here's your steps. First, find any bound you can get. Just some bound. Get a bound somehow. It doesn't really matter how, just get some sort of bound. Then modify your bounds. So I started with a bound I multiplied by x. That was my modification. I got the original function that way. Then I found limits of what was above and below, and because they were the same, that was enough. So I just made a sentence to cite the Squeeze Theorem, and I had the problem finished. Let's do another one. This time we've got the cosine of 1 over x, which is still bounded between -1 and 1. This time we've got x squared, so let's multiply through by x squared. And this really shouldn't look much different. Take a look at these limits. The limit as x approaches 0 of -x squared is 0. The limit as x approaches 0 of positive x squared is equal to 0. By the Squeeze Theorem, the limit as x approaches 0 of x squared cosine 1 over x is equal to 0. The last thing to look at real quick is two special limits that you may encounter, and these are two good limits to know. Limit as x approaches 0 of sine of x over x is equal to 1. Limit as x approaches 0 of cosine x minus 1 all over x is equal to 0. These aren't really very easy to prove, but using the Squeeze Theorem they can be proven. It is a bit tricky though. However, let's see if we can use it. We've got the limit as x approaches 0 of tangent x, and let me write it like this. Tangent x times 1 over x. One thing I know about the tangent function is that there's an identity. Do you guys know what it is? Tangent of x is sine x over cosine x. So we've still got this 1 over x, and now let me rearrange the terms, and now we'll see what we're doing. We've got the limit as x approaches 0 of sine of x over x is one that I'm going to use. And on the other side, I've got 1 over cosine x. So you'll see this is equivalent to what I had before. And just to be careful, this is a product, so I'm using the limit law. I've got this one for sine of x over x is one term. And then I've got the limit as x approaches 0 of 1 over cosine x. I did say that direct substitution works for the trig functions. However, you'll notice in the first one, I get the sine of 0, which is 0, over 0. That's okay though, because I have a special limit up here. It turns out that this limit is 1. And now 1 over cosine x, well, that's just going to plug in cosine of 0. But cosine of 0 is 1, which is fine. So I just get 1. And so my answer is 1.